السلام عليكم ورحمة الله وبركاته. حياكم الله جميعا. نكمل إن شاء الله اليوم دورة ريمانيان جيومتري مع الدكتورة ليانا توبان عبر منصة جسر للتدريب. ونذكر إن شاء الله في رابط حضور حيكون قبل نهاية الدورة. أيضا حيكون هناك بريك صلاة أو استراحة صلاة الساعة 26 دقيقة. الدكتورة ليانا توبان من جامعة الملك سعود، عضو في هيئة التدريس. حياها الله. ويلكم دكتورة ليانا.
Thank you. Hello, everybody. Okay, thank you. I'm going to share this. All right. So we are going to talk today about, hello. So my name is Liana and I work at King's College University. I suppose that this has already been said in Arabic. I'm going to talk today about manifolds and maps between manifolds. I don't know if you are a little bit familiar with this, notions of manifolds, or in between maps between manifolds. If not, that's okay. I hope you already have some basic knowledge in topology, like classical topology. So if you want to ask any questions while I'm speaking, you can simply speak out. So speak, not write, because I'm not able to read the chat while I'm talking. All right. So we are going to talk about. We are going to start with the definition of a smooth manifold, and for this, we are going to define first the topological manifold. You see, a topological manifold will be a topological space with some properties, right? So first condition is for the space to have a topology on it, and we call a space locally Euclidean if around every point you can find a neighborhood which is homeomorphic with an open subset of a Euclidean space, so R to some power. Imagine, for instance, you see, these manifolds can have very weird shapes and very unusual properties in general. But we are going to try to understand them by analyzing, by looking at the so-called local Euclidean spaces with some other properties, with some compatible structure there on, and you will understand in a shortly. So first, we ask for the space to be locally Euclidean. This simply means that locally every space looks like a Euclidean space. Look around you, for instance. Imagine that you are a point on the sphere, which is the Earth. If you look around you, you see, you can imagine a three-dimensional system of coordinates, right? Now, this system of coordinates, so the understanding of the world at the place you are right now, will be maybe a little bit different than the understanding of the world at another point on Earth. But eventually, this can be uniformized, and with this kind of spaces we are going to deal. So local Euclidean means that every point has an open neighborhood which is homeomorphic with an open subset of R or Rn. Now, by open neighborhood, we simply mean an open set containing the point. And a homeomorphism, if you don't know what this is simply a map which is continuous bijective, and its inverse is continuous as well. Now, sorry. Okay. Why is it not working? Sorry, something wrong. All right, very well. So this pair. So remember that we have around the point you have an open neighborhood which is U, and this homeomorphism phi. I'm going to draw again a picture in a moment. It's called a local chart or a coordinate system for the local Euclidean space around the point P, or a local parameterization. Now, remember that we ask for, let me do this. Okay. You see, so we were saying that we have a local Euclidean space, which means that if you take, this is your, say, your manifold, your local Euclidean space. So about any point P, you can find an open set together with a homeomorphism. So a homeomorphism, taking this into an open subset of a Euclidean space. So this is some R. So this is M, your space, this is some N, then, and here you have the image of your point, okay? All right, now it can be proved if you want. So U is taken into phi of U, which is so this is the image, which is a subset of Rn, okay? Now it can be proved that this N here is completely determined by the point P. And then we denote this N by something like this, and we call it the local dimension of the space M at the point P. Now, imagine that you take about the point P another set here, an open set, and you have a homeomorphism. Taking it into a subspace, into an open subspace of some Rm. Okay, imagine that this is, you can do this, right? So this is the image. This is the image of the same of V, well, which is about the point P. But here you have an intersection of this space, right? So the question is, can we really talk about the dimension? Is this N the same as M? Otherwise, you see, if you take the intersection here, then this one would be homeomorphic with a subset of Rn or with a subset of Rm. Well, it can be proved that in fact M and N are equal, right? So under this dimension is correctly defined, is well defined. These two sets will be homeomorphic, right? This one and this one, so they will have the same. They will be subspaces. They will live on a Euclidean space with the same dimension, right? So it makes sense to talk. It makes sense to talk about the local dimension of a space about the point P, and then if this space we are talking about is a connected space and local Euclidean, then the local dimension is a constant, and this is called the dimension on F, and we denote this by the dimension of M. Sorry, we denote this by the classical notation of dimension or something like that, right? We just write it as an exponent. All right, now this pair, right, so about every point P, you have a pair of an open set together with a homeomorphism, right, of between the open set and the subset of Rn of a Euclidean space. This is called a local chart at the point P, or a local coordinate system. And then once we have a local Euclidean space, if we asked the space to be Hausdorff and to have a countable basis of open sets, topological basis of open sets, then we say that this space M is an m-dimensional topological manifold. So I'm going back to this, right? So here we are. Okay, so an m-dimensional topological manifold is an m-dimensional local Euclidean space, which is Hausdorff. You know, Hausdorff means that you can separate any two distinct points by open sets. So you can find two, so if you have two distinct points, you can find an open set about one, an open set about the other, which are disjoint. And then a topological basis is simply a subset of the topology. Remember, that's a topological space, so we know what an open set is, and such that every open set can be written as a union of finite intersection of sets from B. Now, these are good spaces. Topological manifolds are good spaces. They have nice topological properties. For instance, a topological manifold will be always a locally compact space. Now, you know that a space is called compact if any open cover has a finite subcover. Now, it's locally compact if every point has a neighborhood whose closure is compact. Right? So you can find about any point, a neighborhood, and an open set, right? And then the closure will be a compact space. Also, any topological manifold is locally connected. You know, locally connected means that every point has a neighborhood that has a subset, right, contains a connected neighborhood of the point. Then a topological manifold has a property that it's connected if and only if it's path connected. Path connected means that you can suppose that everybody is familiar with the notion of connected. Yeah, it's like one piece. You cannot write the space as a disjoint union of two proper subsets of M. And path connected means that every 2 points can be joined through continuous R. In general, any path connected space is connected, but the converse is not true in general. In topology, again, classical example are the topologist sine curve, the deleted comb space. These are connected spaces, but not path connected. But on a topological manifold, the notions of connectedness and path connectedness are equivalent. Any topological manifold is pericompact. Now, pericompact means Hausdorff, and such that every open cover of the space has a locally finite subcover. So something which is locally finite. Okay, so a pericompact space. All right, so let's go and see some examples for topological manifolds. Now, the immediate example, the trivial examples are any open subset of U is an n-dimensional topological manifold. Of course, that imagine that you have, go back to, here we are. Okay, so suppose that you have U, an open subset of Rn, open, right? This is an n-dimensional topological manifold. Of course, the fact that it's Hausdorff and has a countable topological base of open sets, these are properties which are inherited from Rn, and then every point P, right, can be seen to have U itself as a neighborhood, right? And there is it's homeomorphic with itself, right? So in fact, we can take the map, the homeomorphism to be the identity. Right, so we have one single chart here for the open subset. This is the simplest example of topological manifold. Another example would be the sphere S2 together with the topology of R squared. This is a two-dimensional topological manifold. Two-dimensional topological manifold. I'm going to come back to the sphere a bit later, but here you see we cannot. So on the previous example, we were having one single chart for that topological manifold. Here on the sphere, we cannot have the same neighborhood for all the points of S squared, right? So we have the sphere S2, because the sphere itself is not homeomorphic. This is not homeomorphic with R squared. You know this, right? So this is compact, and this is not compact. Okay, but homeomorphisms would preserve compactedness. So what I'm saying here, we cannot take one single chart for the sphere. So again, I'm going to come back to talk about the charts for the sphere. It's an important example. Well, some other examples here. I'm going to gain some time. Okay, here we are. Some other examples would be something like this: the graph of the function y equals x to the power 3. That's topological manifold. You know, the homeomorphism is given by every point with coordinates x and x to the power 3 is taken into x. That's a homeomorphism. The space will be local Euclidean. Another example of something which is not local, is not a topological manifold, is the so-called Bernoulli-Lemnisky. Think of like a figure 8, diagram here. You have a double point there. This cannot be homeomorphic with a subset of R squared or R or of R cube or something like that, because that double point there it's again, these are properties coming from the topology, from the classical topology. If you remove that point, that double point on the lemniscate, right, then you will get something with, and you look locally about that point which you cut, right, and you will have 4 connected components. But if you remove the image, right, on the disk or a segment or something like that, then you will have 2 connected components or 1 connected components, which preserves this from being from this space from being homeomorphic. So this will not be a topological manifold. Okay, very well. And now we would like to go back to that topological manifold, and as I said, we would like to connect somehow distinct points on the topological manifold. Oh, come on. All right. So suppose that you have something like that, a local Euclidean space, or together with chart, so an n-dimensional topological manifold and the n-dimensional topological manifold. Remember, please, that this means that about every point you can find an open set which is homeomorphic with a subset. Call this phi of u, open subset of Rn. And then imagine that you will take another chart here, so you'll take another open set, and this one will be, as we said, homeomorphic with an open subset of Rn. So open here and open. Okay, then we would like these charts to be what we call compatible. So we would like, if you want, when we move from a chart to another through their intersection, you know, not to have any issue there. We say that these 2 charts are symphony compatible or compatible charts. So the charts are the pairs, something like that, right? So these are symphony compatible or compatible if either their domains, U and V, are disjoint, so either their intersection is disjoint, so then we are done, or if the intersection is not empty, as in the diagram that I've drawn, then when we move from this set to this one and the other way around, right? Then here we'll have something of the form. This is the composition, the composite between phi and psi inverse, and this is the composite between psi and phi inverse. You see, both these functions here, right? So both are defined on subsets of Euclidean. Let me write it here. So this one, they are both defined on subsets of R squared, right? So say we take here just the intersection, we take the intersection here, and then the intersection here, right? So this one will run from psi of the intersection of U and V, which is an open subset of Rn, into an open subset of Rn. So this is in Rn and open, Rn and open. Now here we'll go like this into psi of U intersected V, both open subsets of Rn. We want these 2 maps to be smooth. So the charts are simply compatible if the maps are smooth. If these 2 maps are smooth. You see, these are maps from Rn to Rn. So smooth means that every component is smooth, right? So this we know means that we can compute derivatives, their partial derivatives, and we can differentiate these functions like Fréchet differentiable, right? Now these two maps are called the transition functions between the charts. Okay, and now we are finally ready to go and define a manifold. So we are here, and we say that An atlas on an n-dimensional topological manifold is a collection of charts such that any two are compatible and such that the domains of the charts cover M. So M is the union of the domains of the charts. And then we are going to say that a smooth manifold is an n-dimensional topological manifold together with an atlas. So an atlas is supposed to be maximal. You see, in general, two atlases, we say that two atlases are equivalent if their union is an atlas. So, well, if for the first one, for A1, any two charts will be compatible. For the second one, any two charts will be compatible. But we want compatibility for any chart of A1 with any chart of A2. And now this is so we define the equivalence relation to be given by the union being an atlas, right? This is an equivalence relation, so we can factor in, we can find a maximal atlas. So this is called a smooth structure on the manifold M, and then M together with a maximal atlas is an n-dimensional smooth manifold. And now again, let me. Okay, so maybe here we have an example of two atlases on R for which their union is not an atlas. You see, so they will define actually different, distinct structure, smooth structure on R. So yeah, I want to. This is a simple computation, so it's easy to understand if I. It's easier to understand if I write it. So imagine. Imagine that you have R, right? So this is a smooth manifold as an open subset of R, right? So it's the set itself. So this is, we take A1, an atlas here containing one single chart where phi is the identity, so the homeomorphism is the identity, phi of x equals x. And then we take another atlas to be given, I'm going to call it pi, the homeomorphism given like that, from R to R. Now let me call it psi, as I did it before, psi of x equals x cubed. These are both atlases here, right? We have smooth, we have homeomorphisms from R to R. Now, their union is not an atlas. We need to look at the function, this one and this one, right, in order to see if they are compatible. But this one will be given by psi inverse will be cubic root of x, right? So it's something like that. But this is not smooth, right? At 0, we have an issue at 0 here. So this means that these two atlases are not compatible, right? So not any two atlases on a manifold are compatible. When are they compatible? When this these maps, these transition maps are smooth, right? This will come down, in fact, to the fact that we are going to see that when you have a manifold together with an atlas, right, then two charts, this one and let's say U beta, phi beta, let's say, this will be compatible if and only if. So this will be equivalent with the fact that, well, we take one of them, let's say this one, keep writing this so you get used to this. Again, these are subsets of Rn, so if and only if this is a diffeomorphism. Of course, the inverse of this diffeomorphism is the other transition map, phi beta composite phi alpha. Inverse of this will be a diffeomorphism as well. Okay, a diffeomorphism is bijective. So 1 to 1 and on to smooth. And the inverse smooth as well. Right, so, right. You see, again, these ones are subsets of Rn, right? So this is in Rn, this is in Rn, open subsets of Rn. So we can think of of a function taking some point with coordinates x1, xn here, you see, into a point of the form, let's say, f1 of x, 1x, this is an x, right? f1 of x, fn of x, right, which is here, right? So when is this a diffeomorphism? Is equivalent with the fact that the Jacobi matrix, right? The Jacobi matrix is non-singular, right? So this means that the determinant, suppose you know, but let me just make sure. The determinant of you take the functions here, you see, and you find partial derivatives. So this is not zero. Okay, so something that we are familiar with. You see, we reduced everything. It's like instead of looking at a weird thing with a weird object together with an open subset of topology, you know, from the topology, which can be not very easy to understand, we reduce everything to subsets of Rn, right? Now, just because I'm going to use it, I'm going to need it probably the day after tomorrow, an atlas A on a manifold is said to be orientable. If this determinant, so if the determinant partial derivative is greater than 0 for every x, right, on the domain, so for every x here, right, and a manifold that has, which possesses an orientable atlas is said to be orientable. All right, and now as for examples of smooth manifolds, well, we are going to go back to what we saw for topological manifolds and for local Euclidean spaces, right? A first example of smooth manifold is Rn, right? And here we can take the atlas containing one single chart, right? Then another example, so that would be a first example of a smooth manifold. Another example will be given by any open subset of a manifold. So suppose that M is a manifold, and let's just take U an open subset of M, then U will be a manifold itself. Manifold. And well, an atlas here will be given by, we just take the intersection between any chart of M. So on M we have an atlas, right? So we have on M, an atlas on M will be given by something like that, a collection of charts, right? And then you just take the domains of the chart and you intersect them with the open set, and then you take the homeomorphisms from the atlas of M and you restrict them to the new domain. So this will be an atlas on the subset, on the open subset. The zero-dimensional manifolds are the discrete and countable sets. Every graph of a smooth function, so any function defined on an open subset of, so this is a subset of Rn, open, let's say, right? This subset of Rn. The graph of any function will be a smooth manifold, right? You can imagine it like that. Say this is Rn, this is Rm, and then we take an open set here to define our function, and the graph, right, will be something like this. The graph, right, will contain points of the form x and f of x, right, something like this. This will be a manifold, and many familiar curves, you know, and surfaces from calculus, like the paraboloids and hyperbolic paraboloids or ellipses. These are curves, right? Surfaces, also the ellipsoids and everything. These are all manifolds. Then another example, a little bit more algebraic, would be the general linear group, something like this. This is a manifold. This contains square matrices which are invertible, right? This is a general linear group. These are manifolds, and well, we can see this as the determinant inverse of the inverse of something like this, right? R minus 0, and this can be seen as a function, right, which is a continuous function. So this will be a smooth manifold. Now we have the product manifold. So if M is a manifold and N is another manifold, then their product will be a manifold with dimension M plus N. It's pretty intuitive that if you have an atlas on M containing charts of the form U alpha phi alpha, and then an atlas on N, right? Say we have here charts of the form V beta psi beta, then the atlas on the product will be given by, well, the domains will be products of domains, and the homeomorphism will be this is the definition of the clutter, you know, something like that. So this is defined on phi U alpha times V beta with image here, where a point, point xy, let's say, is taken into phi alpha of x, psi beta of y. Let's really seem easy to show that this is indeed they will, all the properties of the manifolds hold, that any two charts are compatible. All right, and then we finally get to our example of the sphere. So I'm going to spend a little bit more time here. So the n-dimensional sphere. All right, it's a very nice example of a manifold in geometry. So suppose that everybody knows what is the n-dimensional sphere. It contains points such that x0 squared up to xm squared is equal to 1, right? So 1 unit sphere, and this is a subset of R to the n plus 1. And now this will be an n-dimensional manifold, and I will do the computations, or at least I will go fast through the computations with you for the particular case in which m is 2. Okay, so just for you to see, so we are going to work with S2. Right, the two-dimensional sphere. The computations for the general case are, I think I made them on this file that I'm going to share at the end of this course lecture. Yes, you see, I did the I computed everything on this paper right here. So let's try to go together quickly through these computations, but for the small case n equals 2. So this is a sphere, right, and such that x squared plus y squared plus z squared is equal to 1. Okay, so this is a topological space. The topology is the topology of R cube, right? So this is this is second countable. That axioms follow immediately. They are inherited from R3. So we simply need to define an atlas on the sphere for this to be a smooth manifold. So one atlas that we can define is the so-called stereographic projection. The atlas determined by the stereographic projection. So what we do is the following. So suppose that you have your sphere. I'm going to put a system of coordinates here. So this is, you see, not very right. So this is the xy plane, right? That very ugly thing that I drew here. And then we have the north pole of the sphere. So this is the point with coordinates 0, 0, and 1. And we have the south pole of the sphere, which is the point with coordinates 0, 0, and negative 1. And now this atlas will have two charts. So we define UN to be the sphere minus the North Pole, and US to be the sphere minus the South Pole. Now, both are open sets of the sphere, because the sphere is closed, right? It's compact, so we take a point, remove a point, we get an open set. Now, they are both subsets of the sphere and open. Now, we need diffeomorphism, we need homeomorphism here, and these are the stereographic projection. So we define pi n here from un into r squared. So this will be pi n of un, which is a subset of r squared, like that. Every point of the sphere, so point with coordinates x, y, and z, I'm going to call it P, this point, is taken through this stereographic projection into the intersection between the line determined by the North Pole and the point and the xy plane. So this point here, so this is pi n of P, right, of the point P. And we define the same, the stereographic projection through the South Pole. Sorry. So every point of the sphere, right, will be taken into the intersection point between the line determined by the point and the South Pole, and you see, if this is the point Q on the sphere, this one will be pi s of Q. Okay, so the applications are very defined in a very geometric way. And now, in order to find, the analytic, the coordinate expression of this application, we simply write the equation of the line passing through n and passing through p, right? It will be something of the form. So I'm going to find pi n of p, the algebraic expression of the stereographic projection. So if p is of the form x, y, z, right, then the equation of the line np will have some parametric equations of the form x equals to, I'm going to call it like, let's say, t times x, right? It passes through n and through the point x, the first x, the first coordinate of the point p. Then y will be of the form t times y, right? And z, well, there is a coordinate for n here, so it's 1, which is not 0, plus t times z minus 1 is something like this, right? So this is the equation of the line np, and then we want to intersect the line n. We want to intersect the line np with the xy plane, right? So this means that we take the z coordinate to be 0, which means that 1 plus t times z minus 1 is 0, and this will give us a t, the parameter corresponding to this intersection point, to be 1 over 1 minus z. Okay, and now this means that I'm taking t, I'm plugging it here, so x will be x over 1 minus z, and this is z, and y will be y over 1 minus z, which means that we can see, the analytic form of pi n to go like that. Pi n, find on un into pi n of un, subset of r squared, given by pi n of a point with coordinates x, y, z. So this will go into x over 1 minus z. I'm just taking these points. This is y over 1 minus z, and well, the third coordinate is 0, so we don't write it here, right? Z is not 1, so it makes sense to talk about, to divide by 1 minus z. Z is not 1 because we define it on un, we define this application on un. Un had s squared with n, the North Pole removed, so this point is not on the domain, right? So z cannot be 1, right? So this is how we defined pi n, and then similarly we find the stereographic projection from S, and with the same kind of computations we get something of the form x over 1 plus z, y over 1 plus z. Now here z is negative 1, which again is okay because we removed the South Pole, which was the only point having the third coordinate z coordinate to negative 1. So we have analytic expressions for these functions, and then we define the atlas on the sphere to have two charts. So this one and this one, well, I call them right? So pi. Okay, pi and US with the stereographic projection from. Why it's not writing? Okay, so something's wrong. Well, all right, let me go back to this one. So just to show you that, you see, when we are in higher dimensions, right? When we are on higher dimensions, so this looks a little bit the same, right? This is the inverse. Sorry. Okay, here we are. You see, the stereographic projection from the North Pole, it's 1/1 minus xn, the last coordinate, and x0, x up to x minus 1, and the stereographic projection from the South Pole will be given by something similar with what we found for the case n equals 2. Now we can find the inverses of these matrices, of these applications of this homomorphism, and then okay, so something wrong here with the okay. I'm going to go back to this. Okay, we can find the inverses of these maps. Okay, and they look like this. So for the case n equals 2, you just take the first two coordinates, right? And then it's immediate to the fact that it's immediate to the fact that the union between SM and SN, you know, so the first one is the sphere without the North Pole, the second one is the sphere without the South Pole. When we take the union of these, we cover the whole sphere, and then we simply need to show that the charts are compatible. So when we compute the composite between one homomorphism and the inverse of the other, computations show that this looks, the analytic expression look like this, right? So, well, shortly it can be written as, you know, y over the length of y squared. This is y1 squared plus up to the last one squared, and this is clearly smooth. That y, you see, cannot be 0. This is never 0, so that's all right. So indeed, the sphere is a manifold, is an m-dimensional manifold, and what you saw here is the atlas given by two charts. There is another atlas that we work with on a sphere, which is an atlas given by two m+2 open sets, and so we define them. Again. I'm trying to. What's wrong here with my? Let me try to go back here. All right. So, no, I cannot. Let me do this. Sorry. What do you see? I'm sorry about this. Hello. Can you hear me, please? Hello. Hello. Yes. No. What's wrong with? Bon.
Yes, Doctor, there's nothing.
Can you see me? Can you hear me?
Yes, I hear you, but there is no.
What about now? Yes, some technical issues here. Yes, is it okay?
Okay.
No. Yes, all right. Okay, very well. So, okay, so we can define another atlas on the sphere, having more charts, and then just the charts are given like this. So, no, okay, I'm going to come back to this. Anyway, bottom line, this new atlas will be compatible with the first one, and then in fact they will determine the same structure, the same differentiable structure on the sphere. Yeah. So it's really weird here. Okay. Another something. Oh, okay. Now it's. Okay. Oh yes, so I did make a picture here for the other atlas. You see, for every you split your sphere into the upper sphere and the lower sphere, and then for every coordinate you do this. So every time, so for a point on the sphere will have, say, n-dimensional sphere will have n+1 coordinates, right? So you will have for instance, for x1 equals 0, you split into upper sphere and lower sphere. Then you take x2 equals 0. This will give you x2 greater than 0 and smaller than 0. So two demisphere and so on. So you'll have 2 times n+1, so 2 n+2 demisphere. This will be the domains of the charts. And now we are going to define the homeomorphism on the charts by taking, if you look at the green chart, you take every point on the green chart, you simply take the orthogonal projection on the on xi equals 0, on the plane that cuts the sphere into 2. And from the blue chart, you do the same thing. You take orthogonal projection onto that plane that cuts the sphere into 2. So these are homeomorphisms from those open sets, right, into onto open subsets of Rn, right? It's easy to imagine that you take a sphere, say it's made in rubber, so you cut it into 2 demispheres, and you imagine that you flatten it. This is what you are doing, right? So this will go onto that cutting plane. Now it's pretty easy to check. Let me see if I didn't. It's pretty easy to check that the charts are compatible here. Then indeed you have an atlas, but every chart on the previous atlas, the one for which we did some computations, will be compatible with every chart on this atlas. So they do determine the same smooth structure on the sphere. Now, do remember that when you have 2 manifolds, their product will be a manifold. So this means that if you take, for instance, R, which is the real line, right, which is a one-dimensional manifold, and the sphere, the circle, right, what you get when you take their product will be a cylinder, right? So this is a 2-dimensional manifold. That the dimension of the product is the sum between dimensions of the 2 manifolds. Another manifold would be the torus, right, which is defined to be S1 times S1, the product between the circle and the circle. That's a 2-dimensional manifold. This looks like some sort of a donut, right? The torus. Now, so a lot of examples here. Now, another important example would be the real projective space. Now, this is the space. This is the space of if you think of the lines of all the lines passing to the origin of Rn+1. So I think I wrote it here. So the projective space, the set of all the lines passing to the origin of Rn+1. Now this can be seen as a quotient space, right? So you take any 2 points and you define an equivalence relation saying that 2 points or 2 vectors or Rn+1 belongs to a line. They are equivalent if they belong to a line passing through the origin. So you will define an equivalence relation like this, and then when you factor the space Rn+1 with the you remove the origin and you factor it with this equivalence relation, what you get is something called the projective space, and we can define using quotients and the quotient topology. We can define homeomorphisms, charts on this space, and homeomorphisms. So we can define an atlas here, and we give this space a structure of a manifold. Okay, so if we have time, then I'm going to come back to this projective space sometime, a little bit maybe tomorrow or the day after tomorrow. It's just for you to have an example of a space which is a little bit less trivial, the projective space. All right, now finally we are able to go and talk about smooth maps between manifolds. So just to I'm going to try again to, something's wrong with my, okay, all right, so just to make you remember what we were talking about, we know now what a manifold is. So again, what is a manifold? Well, this is a topological space which is local Euclidean. So about every point we can find a chart which we can find an open set which is homeomorphic with an open set of Rn, and then we define a collection of charts compatible. To get every chart comes with a homeomorphism, and the charts are compatible. So when you take the composite between one diffeomorphism and the inverse of the other, you will always get diffeomorphisms between Euclidean spaces. Then we would like to define maps between manifolds, and we are going to do, as we always do, we are going to translate everything in the language of maps between Euclidean spaces. So we say, so suppose that you have two smooth, right? So instead of talking about a map between a sphere and the projective space, for instance, right, which are two manifolds, we are going to translate everything, to turn everything into a language of a map between, well, S2 is a two-dimensional manifold, so this will be R squared, and the projective space is an n-dimensional manifold, so between Rn. So instead of talking about maps between manifolds, we are going to talk about maps between Euclidean spaces. And now we are going to say that a map between two manifolds is differentiable if something like this. F phi psi, I'm going to show you what this is differentiable at the point. So we are here, you see. So you have your map F going from M into N between two manifolds, right? Then instead of looking at the point P, we look at a neighborhood of P, right? At this open neighborhood of the point PU, which is homeomorphic with a subset of Rn, and then again, V, an open neighborhood of f of P is homeomorphic with a subset of Rn, and then we are going to say that f from M to N is differentiable at the point P if in fact just imagine that you drag your map F down to get a map between Euclidean spaces, so you will get this F that we denote by F phi psi, which is the composite between psi, F, and phi inverse. This will be a map going from phi of u, which is an open subset of Rn, into psi of v, which is an open subset of Rn. So if this map is differentiable, Fréchet differentiable at phi of p, we say that the original map F is differentiable at the point P. Right? We ask for F on the definition to be continuous just to ensure that that F inverse of V that you see on the, on the first row of this page is open in N, right? And a smooth map, what we mean here is that when we talk about a smooth map between manifolds, then we assume the map to be continuous, right? By definition. Okay, now as I said, this F, that local, we call it the local representation of F in the local charts, right? This is differentiable map between open subsets of Euclidean spaces. Now the differentiability of a map at a point is correctly defined. This means that if you take another chart around P and another chart around V, right, so other charts and other diffeomorphisms, then the representation of F, the local representation of F in these new charts will also be differentiable. So this is what I'm writing here, right? Imagine that psi 1 and phi 1 are other diffeomorphisms, homeomorphism, right? So you have the same situation, but for other charts, U1, phi 1, V1, psi 1, then you have this relation between the two local representations of F on the local chart, right? F phi 1 psi 1 and F phi psi, but these maps here, phi 1 and composite phi 1, psi 1 composite psi inverse and phi composite phi 1 inverse are smooth because they are composite of smooth functions. So if the local representation of F in the charts phi psi is differentiable, is a differentiable function, then so is the other one in the charts phi 1 psi 1. By this we simply mean that it's correct, it's well defined, it makes sense to define the differentiable of a map between manifolds via the differentiability of the local representation of F in local charts. Now we have immediate properties saying that if you have two smooth maps and their composite is smooth, again I write here the local representation of the composite. So this is an immediate result. Now we say that a map is a diffeomorphism between smooth manifolds if it's bijective and both F and F inverse are smooth. So again, when we talk about F and F inverse smooth, we think at their local representations, their representation in local charts. So we talk about Frechet differentiability. Now, if there is a diffeomorphism between two manifolds, then we say that the manifolds are diffeomorphic. You see, we can prove that the homeomorphisms from the definition of the charts on a manifold are in fact diffeomorphisms. So if you take a chart, right, a chart, so being from an atlas on the manifold M, then this map phi is a diffeomorphism, and it's pretty easy to write phi in local charts and to show that it is indeed a diffeomorphism. Now we have some notations here. We are going to denote by C infinity from M to N the set of all smooth functions between the manifolds M and N, and by f of m, the set of smooth functions from M into R. Remember that R is a manifold. Now, this set of smooth functions defined on a manifold with values in R has a structure of an algebra, of a real algebra. The operations are defined on the classical way, so pointwise, right? So you see, we have a lot of algebraic properties here on geometric objects. All right, so there is a lot of, before going to the tangent space, there is a lot of information that you heard here. I would like to take some examples and to show that, for instance, these two maps are, or at least, well, these two maps are smooth indeed. So we can see how we write maps in local charts. I'm having, unfortunately, some issue with the screen touch. So I'm going to get out of this and come back in 1 second, please. Please, I'm really sorry about this. Hopefully it will. I can touch this thing. What's wrong?
Okay, Doctor, no problem.
You see something's wrong with my touch screen. So I'm going to be back in 1 minute. Really sorry about this.
No problem.
I cannot even, okay. All right, sorry about this.
دقائق في انتظار انضمام الدكتورة ليانا.
Hello, sorry, I'm really sorry about this. I don't know what happened. It's like somehow my computer seems to. Can you hear me?
Yes, yes, we hear you.
To have decided to make an update right now, so that it blocked everything. Sorry about this. All right, so I'm going to take these examples, right? So first we want to show. No. So we want to show. Oh no, what's wrong with this? Can you see my white screen?
Yes, we see.
Yeah, but for some reason not working. So. Okay, so look, I'm going to come back to this. Let me think. I'm going to come back to share. Okay. Okay. No. All right. Okay. Now I'm going to try again. All right. Let's see if it allows me to. No. Anyone knows what's wrong? Why it's not working?
You use the pen of this one?
Yes, but for some reason refuses to work. Okay.
Write on PDF, Doctor.
Sorry?
You can write on PDF.
No, it refuses to work altogether for some reason.
It worked before, يعني.
I know, but
I don't know what's the problem.
I don't know either.
Try again.
Yeah, I am. Okay, so again. Yeah, not working. Okay. Sorry. All right, so look, what I'm going to do is to keep going and talking about, and hopefully during the break I'm going to make this work.
Okay.
Okay. All right. So, all right. So, zoom. Where is the zoom? I don't know what's wrong, honestly. What do you see now on the screen?
Black. It's black.
Black. Okay. All right. What about now?
Now you share maybe
Yeah.
it's PDF.
Okay. So the second part of this presentations would be about the tangent space at a point to a manifold. Now, okay. All right. So we are going to do this. We are going to do this by defining something called the germ, the germs of a point. So suppose that you have two manifolds M and then we'll take the set. We'll take this set L of P containing all pairs of functions together with an open neighborhood about a point P of the manifold M, and then on this set, so imagine that you have a manifold, think of a sphere, for instance. You take a point on the sphere, you take an open set about the point P, and then you define the map from that open set into the other manifold, right? Think of R or any other manifold. And then you take pairs like that, and we can define an equivalence relation on this set. And we say that two pairs are equivalent if you can find an intersection, an open intersection of the two domains, right? So you have a point, you have an open set about a point, another open set about the same point, and you take an open set of the intersection of these domains such that the functions are the same, restricted at that open set. So these are this is an equivalence relation, and when you factor the set with the set of those pairs with this equivalence relation, what you get is the set that we call the set of germs of smooth functions or of smooth maps from M to N, right? Then I'm giving here an example, you see, so you see that it is somehow familiar once you think of functions. If you think of the function 1 over 1 minus x, and the function, so imagine that you expand this, right, in this series, so this is 1 plus x squared, so on, and so on. Then at any point of the domain, so we know that this converges, right, for x between -1 and 1. So for every point between -1 and 1, the germ, these two functions, f of x and g of x, have the same germ. So in fact, what we mean by this is that instead of working with equivalence classes, we are going to work with the function itself. So we suppose that when we define a function on a manifold at a point, then you define it on a small neighborhood about the point. You think that the function is defined on a small neighborhood about the point, and then this is the function you are working with, right? So, but it comes as think of it a little bit of it as a representer of an equivalence class, but except that every representers of those equivalence class about a point are the same, right? They are defined, they're the same on a small neighborhood of the point. And now we denote the set of all the germs of functions from M to R, M being a manifold, to R, right? So the codomain is the set of real numbers by something like this, right? Either C, P infinite of M, or G of P, G from germs. And now this is a real algebra. The operations, again, are the natural operations, right, pointwise. And then, again, we talk about germs of real functions, but we identify a germ with the function itself, right? So instead of thinking equivalence class, we think of representer of that equivalence class. And now, every germ of function will induce a morphism of algebra. So again, these are this C infinite, CQ infinite, CP infinite of M and M. They are algebra. So we can induce a morphism between these two algebras defined like this. This is called a pullback along the function f, and it's a pretty important notion. We are going to use it again when we have all these notions defined. You see, so if you can look at this diagram here, so f is a function going from M to N. M is a manifold, N is another manifold, right? P is taken, so P is a point, you fix a point on the manifold M, and Q is its image via F. Now, remember that we identify a function with a germ. So in fact, when I'm talking about this psi bar, this is a germ of a function from N to R, right? So at the right of the diagram. So this is a germ, equivalence class. So again, soon we'll drop the germ, this germ notation, and we talk about functions. So we can look at this diagram, which is commutative, and we define f star to be, you see, f star will go from the algebra of germs at N into the algebra of germs of M, and then every germ psi star is taken into f star, the pullback along f of 5 star, defined as we've seen here. So it's the germ of psi composed to f. Now, immediate function, you see, I wrote it here. defined. I wrote the definition of the pullback along phi without that heavy notation of the germ. We have immediate properties, functorial properties for the pullback. The pullback of the identity is the identity of the algebra of functions defined on M. The pullback of the composite is the composite of the pullbacks backwards, and then for every local diffeomorphism at a point P, its pullback is an isomorphism of algebras. So a local diffeomorphism is simply a map which restricted, for which there is an open neighborhood about the point P, such that the restriction of F to that local neighborhood is a diffeomorphism. So a local diffeomorphism induces an isomorphism of algebras. And then, all right, so I'm writing here. So the first properties are absolutely trivial. They come from the definition, while the last ones come from these commutative diagrams of the. Right, so here you have a commutative diagrams F and F inverse. Their composites, left and right are the identity. So when we go to the algebra to the level of algebras, then we are going to get that indeed the pullback of a local diffeomorphism is a bijective function, right? And now using germs, we are going to define a tangent vector to a manifold. So suppose that you have a manifold, and then you take a point on the manifold. So again, think of a sphere. If it's easy for you, take a point P. We would like to see what is a tangent vector at P to this manifold. We also call it a derivation of algebra of germs. So this is simply a map which is linear and which satisfies the so-called Leibniz rule. So XP, this is defined on the algebra of germs with real values. So XP acts on the product of two germs or two functions. Remember, we identify germ with any function there on the germ of the product. This is XP of F times G of P plus F of P XP of G. Think of this, if instead of this notation XP of FG, you think of notation, think of, real analysis, prime, the prime thing, right? The derivative. This is like saying FG prime is just for you to, to see that this is a natural extension of the derivations, right? So it's like saying FG prime equals F prime G plus. So Fg, everything prime, the derivative of the product is F prime G plus Fg prime. So something like this is called a tangent vector. So again, a map which is defined on the algebra of germs, so it will apply, a tangent vector will act on a germ, on a function, and then it's linear and satisfy this Leibniz rule. And now the set of all tangent vectors to a manifold to a point P is called the tangent space of the manifold at the point P. And we are going to see that we are going to put a structure on this tangent space. So first of all, this will have an algebraic structure. It will be a vector subspace of the dual, algebraic dual of the set of smooth functions defined on M, and then that this is immediate, so it's a vector space itself, which means that it makes sense to try to talk about the basis for this vector space and to try to find a dimension for this vector space, right? Or algebra, linear algebra on this space. Now, just to start with, if you have a tangent vector at a point at the manifold, and the germ determined by the the constant function there, then XP of this alpha is 0. Again, the proof is immediate. I'm going to prove almost nothing on this thing. So a tangent vector applied on a constant function, the germ of a constant function is 0. It's like saying that the derivative of a constant is 0 if you always think of that extension that I was talking about. All right, and now this this tangent space, the tangent space will allow me now to define the differential of a map, of a smooth map between manifolds, and or the tangent map. So suppose that phi is a smooth map between manifolds M and then you have a corresponding morphism of algebra, right? So that phi psi, the pullback, going from the maps, smooth maps on N into the smooth maps defined on M. And we define the tangent map or the differential of phi at the point P to be the map going from the tangent space at the point P in M of M into the tangent point of QQ is just the image of P through phi at N. Defined through this, you know, the differential of phi P of XP is XP composite phi star is a pullback. And then this actually is a map that takes a tangent. We are going to see that this happens indeed, that takes a tangent vector at the point P to the manifold M into a tangent vector at the point Q, the image of P, to the manifold N. Again, imagine that you have a map going from a sphere to sphere. You take a point on the sphere, and then the image of this point on the codomain, right, on the other sphere, and then we somehow define the differential between the differential of our original map to somehow take a tangent vector to the first sphere, to the point P of the first sphere, into a corresponding tangent vector at the image of the point P onto the codomain sphere. So the definition is here, and I try here to make some diagrams, so this is this can be understandable. So indeed, you see, so remember that we defined the differential like this. So we want indeed to see that this is correctly defined, that this XP composite pullback phi star is indeed a tangent vector there at N, and it is, right? It's linear and verify Leibniz rule. That's something that can be checked. And then we are going to see that this will be a homomorphism of vector spaces. Remember that the tangent spaces have both a structure of vector spaces, like linear vector spaces, and subspaces of, vector spaces. Then again, we have functorial properties of the differential. The differential at the point of the identity is the identity of the tangent space. We have a chain rule here. The differential of the composite is the composite of the differential, and then, well, with corresponding points, you just translate the points, and then if f is a diffeomorphism, that the differential of f at any point P will be a linear isomorphism, an isomorphism of vector spaces. The inverse of the differential is the differential of the inverse. You see, these are properties that again should be familiar from linear algebra. They are extended here to geometry, and all the definitions all the constructions that we are made on manifolds are made such that the classical properties that we know from when we apply linear algebra here remain valid. Okay, then if we have a smooth map which is a local diffeomorphism, remember, so we know that this theorem happens if f is a diffeomorphism. So if f is a diffeomorphism, this is what we saw previously, that if f is a diffeomorphism, then its differentiable is an isomorphism. But it also happens for a local diffeomorphism only. So the function f, the map f, is not a global diffeomorphism, but only locally. So so its restriction to an open neighborhood of the point P is a diffeomorphism. Then again, yet its differentiable will be a diffeomorphism. I think it's 6:20 and we have a break, right? All right. So I will try to sort out the thing. Okay, so I will see you in 20 minutes, right?
Thank you, Doctor. Now
Thank
break.
you. I'm sorry for this. Yes, for these technical issues. All right.
No problem. 6:40 inshallah we will back.
I'll be back. Thank you.
إن شاء الله استراحة الآن وسنعود 46 دقيقة بعد صلاة المغرب. حياكم الله جميعا. السلام عليكم ورحمة الله وبركاته. نكمل دورة هندسة ريمان مع الدكتورة ليانا. Welcome back دكتورة.
Yeah.
Welcome.
Should I start or wait one more minute?
Wait إن شاء الله. خلاص 40 بإذن الله.
Okay.
One minute more دكتور إليانا because the student not coming.
Sure.
Welcome back دكتورة. You can start now.
Okay. So I would like to, go back to those examples of differentiable maps so you can see what we mean, computation. So I'm going to remind you what a differentiable map between manifolds is. So suppose that you have a map defined from a manifold to another manifold, and we say that f is different, so P is a point of M, right? And you have the image of the point. And we say that f is differentiable at the point P if the map, which is called the local representation of f in some chart. So if there exists, let me write it properly. If there exists, and this will turn into for any, as we saw, if on a chart about P, in a chart about Q, which is f of P, such that the local representation of the function in this chart, which by definition is this function, this composite, this will defined on phi of u into psi of v. So this is a subset of Rm, say this is of dimension m and this is of dimension n. Open here, open. Differentiable, Fechet differentiable. So again, picture will make us understand a little bit better. So this is, say, a manifold M. You take point P. This is the manifold N with its image, right? So f of P. So the function f from M to N will be differentiable at the point P if you can find a neighborhood, an open neighborhood about P, together with its Diffeomorphisms or local chart, we say, about the point P. This will be okay, this is U. This will be the image, and this is a subset of Rm open. So you have here phi of P, and then you can also find a chart here about the point f of p with a corresponding diffeomorphism, which will take this into psi of v. So this is psi of f of p, right? Okay. This will be open in Rn. So you see, you can take this map going from this space, right, between open sets of Euclidean spaces. So this is what we call f phi psi, the local representation of f in these charts. And this is by definition psi composed to f composed to phi inverse. So if this is differentiable at the point f of phi of p, then f will be differentiable at p by definition, right? So again, it's like you drag this one, instead of looking at m and n, you look at their local, you look at them as locally Euclidean space. So you look at maps between Euclidean spaces. And now there are some examples on the file that I prepared for you. First example is to show that the function f defined on R3 with values on R squared by f of x, y, and z equals to x plus y plus z minus 1 is differentiable. All right, so we say that the function is differentiable on a manifold M when it's differentiable at any point of M, like the classical way we define all these kind of notions. And now you see, we look at this function as a function between manifolds, but R cubed and R squared are manifolds, each having one single chart. So here the chart on the manifold R cubed is given by R cubed together with the identity of R cubed, right? So just one chart. Here we take the chart with one domain R squared and the identity of R squared. So in fact, when we write f in the local charts, you will take f, right, in the local charts, identity. So this will be identity, composite f, composite identity inverse, which is still the identity. So this will give us eventually the same f, right? So in fact, instead of looking at f of x, y, and z defined like this between the manifold R cubed and R squared, we look at it as a function defined between Euclidean spaces. So how do we check if this function is differentiable? We simply look at the partial derivatives, right? What is the partial derivative of x plus y? So with respect to x, this is 1, right? Partial derivative of x plus y with respect to y, this is 1. With respect to z will be 0. Then they are all differentiable. This one with respect to y, x, y, and z are all 1. Everything is differentiable, so your original function is differentiable. But now, what if we take, so this is now nothing new here, I guess, for you. But what if we, instead of defining the function from R cubed in R squared, we define it from the sphere into R squared? Right? The same expression, identical expression for the function, but the domain is not R cubed anymore, but R squared. So again, the same function here, x plus y plus z minus 1, right? So the domain is not the same. Now this is a map between manifolds. In order to check whether this is differentiable, we need to go and write local charts. We need to go through all this local representation of the function. So we need an atlas here. We are going to take the atlas that we talked about, the stereographic projection UN phi n, together with US and phi s, North Pole, South Pole. And now for R squared here, we take the chart containing the atlas containing one single chart, the whole R squared with the identity. Of course, we are always going to take, there are more complicated atlases on R squared. We are always going to take the simplest one, right, to simplify the computation. So in order to check whether f is differentiable at a random point xyz of R squared, we need to write the local representation of the function. So we need to write down something like this, okay? So we are going to write f on the local chart. So we take, sorry, I'm just, okay, we take an arbitrary point here, x, y, z on the sphere. All right, so we have the sphere, very beautiful sphere. And then we take a random point x, y, z. And you see, it will be either on UN or US. So let's suppose that this point is in, so assume that XYZ XYZ is in this one, right? So this means that the point XYZ is not the North Pole. So this simply means that Z is not equal to -1. Then we should do the same thing for by assuming that it's not in US. But one computation will be enough for you to understand how it works. So we need to write down the local representation. So we need to write down local representation of F on this chart, right? So we look at F represented on pi n and the identity of R squared. Now this is by definition the identity of R squared, composite F, composite with the inverse of this stereographic projection from the North Pole. This is defined on pi n of un, right, into the identity of R squared, right, applied on R squared. Now, pi n of un, do you remember what is pi n? Pi n is pi n of a point is the intersection point between the line determined by the North Pole and that point and the horizontal plane, the plane z equals 0. So n is not in the domain. So the only point that cannot that it's not on this plane is the origin, right? Only the origin is not an image. So by this I mean that it's very easy to see that this is simply R squared minus 0. By 0 I mean 0, 0, right? The point with coordinate 0, 0. So let's write down what is this? What is the identity? Composite F, composite with the inverse of the stereographic projection from the North Pole of a point x, y, and z. Well, this is the identity, composite F of pi n of x, y, z, pi n inverse of x, y, z. Sorry, this is x, y, not x, y, z, right? There's no z here, huh? Okay. Only two coordinates here, applied on pi n inverse y, x, z, x, y. So this is what I wrote this, and then, all right. So this will be what? This will be identity of R squared, composite F of now pi n inverse. We did compute it together. At least we had a try to this. This is 2x over x squared plus y squared plus 1, 2y over x squared plus y squared plus 1, and x squared plus y squared minus 1 over x squared plus y squared plus 1. Okay, now we apply F on this triple, so that is the identity of R squared. Of F applied here, so I'm looking at the expression of F. First component is x plus y. I mean the first plus the second component, right? Which means 2x plus 2y over x squared plus y squared plus 1. And the second component is the sum of the three of them minus 1. So this will be 2x plus 2y plus x squared plus y squared minus 1 over x squared plus y squared plus 1. And there is a minus 1 here from the definition of the function. Now, this is obviously, so identity applied on this function gives you the identity, gives you the same thing. Okay, this gives the same thing. So this will be obviously smooth, right? This is like polynomial, algebraic rational expressions, right? So no problem in showing that the function is differentiable, right? So what I meant by this is that when the function is defined between manifolds, in order to check whether the function is differentiable or not, you will need to translate everything. You need to write the local representation of the function. Okay, so I was talking about it before my computer decided to take a break. All right, so now I'm going back to. Do you have any question on this first part about manifolds of the presentation? Any question? So then we moved on to the tangent space at the point. And I'm going to remind you very quickly now that I can write what is this. So we would like, so suppose that you have a manifold, right? A manifold M, and you take a point on the manifold. Okay, now we want geometry on this object, right? So we would like to define tangent vectors to the manifold. Now we define them a little bit. There is another interpretation, as you will see in probably in the last lecture, the day after tomorrow, for these tangent vectors. But now how we introduce them. So you see, imagine that you take functions going from M into R, right? The set of real numbers. Now M is a math, so we take some functions here, okay? Something like that. Then these functions, so smooth functions, smooth. So again, smooth functions between manifolds. M is a manifold. Now imagine that on this manifold, you take here about the point P an open set, right? So you have an open set, and then you define f on such that is defined on that open set. And now you take another open set here about the point P, and let's say you define another function g, which is smooth. Now we say that this function f and g are equivalent, and they will we are going to their equivalence class will be called a germ of functions fp. These are equivalent if they are equal, you see, when you restrict them to the intersection. And now you take open sets here and you restrict at the intersection of everything. And then, in fact, when you think of a function defined on a neighborhood of the point P on M, you think of all that equivalence class, all the functions which are on that neighborhood have the same value there. So this is what we mean by a germ. And now, you define the set of all the germs, right? And this is what we denote by something like this, right? So this contains all germs of function of M, defined on M, with real values, right? If you think of equivalence class, you put a bar here. Otherwise, if you just think of a representer, then you ignore the bar, right? And then that's very important. This is a real algebra. So all the smooth functions, smooth functions like this. This is a real algebra. The operations are the natural ones. F plus g at p will be f of p plus g of p. The same for the product. The same for scalar multiplications. And now, so the elements of this set are germs of real functions. But again, we drop it and you identify a germ with a function itself. Now, again, very important is that whenever you define a germ between two functions, so we can define it not only with values in R, but with values, we can find germs with values on another manifold. And then suppose that you have a function, right, going from M into N. Here you take a point, P. Here you take a point P in M, and then you take Q to be the image, f of P, right? Here. So M and N are smooth manifolds. And now, all functions like this, or the germ corresponding, if you think of functions, will induce the so-called pullback, the pullback. We pull back the function, okay? This is exactly what you are doing. So it's the pullback along F. And this is defined, this is a function we denote it by something like this. You will see there are two kinds of functions in this geometry, either pullbacks, where you have a star, which is an upper index there, and the push forwards, the functions that push the functions forward, we denote them with a star down, okay, with a lower index there. So we denote, this will go from the functions in smooth functions or smooth germs of function at n into smooth functions at m, and we define it like this: f star of a function here of some psi is psi composed to f. So the pullback along f. So if you want to understand, you can draw a diagram here. So here you take the manifold M. I'm putting the point P here, just it's just to show that the point here, the point P belongs to the manifold M. Then you have N, and this is Q, which is f of P, right? The image of the point P to f, and then you see, you take a germ here, so this means, or a function if you want, in C infinite of n, so this means a smooth function defined from n to r, right? So psi is simply a function defined from n to r, which is smooth, right? So the image here, the point, will be psi of q, and then you close this diagram, and when you take the composite between psi of and f, then you get this function, a smooth function going from m to r, and this is what we denote by f star of psi. This is the pullback along f. Okay, so this is f psi of star. Okay. So we are going to use this a lot, and we actually use it first thing we are going to use it in order to define the tangent map, the differential of a function, right, or the tangent map between two manifolds. Now, before this, we still don't know what is a tangent vector, so we are going to go in. So remember, we want to see if M is a manifold and P is a point of a manifold, what is a tangent vector at the point P to the manifold? Something that we represent something like this. And so we take M, we take P, a point, and then we take this algebra of functions defined on M, function defined at P. If you want, think of function. If you want, think of a germ. It's maybe easier at this level to think of functions. So we say that a tangent vector of P, a tangent vector at P, a tangent vector to the manifold M at the point P, we also call it a derivation of the algebra of germs, is a map, I'm going to call it XP, defined on smooth functions of M with real values, right? So this XP will act on an element here, which is a function defined on M with real values. So again, remember, this means the set of all smooth functions from M to R, smooth functions. So I want this XP to be linear. XP is linear. So this means additive and homogeneous, right? So this means that when you take XP of F plus G, this means XP of N, real N, and the same for like that. This lambda is homogeneous. Functions defined on N. So linear, and second conditions that we want for a tangent vector is that XP satisfies the Leibniz rule. Right? This means that when you calculate xp on a product of functions, then this will be x applied on f times g plus f plus f times x computed at g, right? This is what I was saying is like some sort of fg prime equals fg prime plus f prime g. All right, so something like this is called the tangent vector to the manifold at the point P, and of course we are going to denote by TPM the set of all tangent vectors at the point P to the manifold. So all maps like that, linear and satisfying Leibniz rule. Okay, so the tangent space is the set of all tangent vectors. And now it's pretty easy to see that this space is a vector subspace, so vector size like in linear algebra of the dual of this space. If you are not familiar, the dual of a space, so in general, the algebraic dual of a space is simply the set of all linear maps defined from the space into R. So being a vector subspace, it's a vector space itself, right? So this one is a vector space, has a linear structure, right? It's like when you think of vectors in R-squared, think of vectors in R-squared, right? We know how to add vectors, we know how to multiply a vector by a scalar using, for instance, parallelogram rules or something like that for addition. Okay, so we'll have an algebraic structure, a linear structure on the vector space, on the tangent space at the point P to a manifold. And now, once we have the tangent space, we can go and define the differential of a map defined between two manifolds, right? So suppose that you have a function f which goes from a manifold to another manifold. Okay, so we would like to define the differentiable. So suppose that P is a point here. Suppose that its image f of P is some point Q, which is f of P. And then remember that a function induces pullback. So you will have something like this. So every f will get a pullback. We just defined it somewhere here, right? So it goes from the real algebra of real smooth functions defined on n into its contrariant, right? You go back, so you go like that, and well, remember this is f star of some function here, right? Was psi composed to f, was defined like this, and then we are going to define here the differentiable, the differential of f at P. So it's denoted either by the differential of f at the point P, is denoted either by this or by this, or it's also called the tangent map of f at the point P. So I want this function. It's also denoted by something like this. So the differential of f at the point P, I want it to go from the tangent space at the point P to the manifold M into the tangent space at the point Q to N. Remember, Q is the image of f, so of P. So what I want, I haven't defined it yet, I will. So what I want is this. So this is your manifold M, this is your manifold N. You have a map between them. This is a point P, this is its image, f of P. So I want the differential to go from the tangent space at P to the manifold M into the tangent space of f of P to the manifold M. So I want a tangent vector here to go into a tangent vector. I'm going to call it U, a tangent vector. So this Q is f of P here, right? So this is my goal, and we are going to define this like this. So the differential, so it applies, you see, on an element here, so on a tangent vector at the point P to the manifold M, and we define it to be xp composite the pullback of f. So something like this. And now, first of all, let's see that indeed, right? So this is the definition of the differential of f at the point P. Now let's see that indeed, you see this guy here. So this is for point P at M. So first remark here is that indeed this guy here lies here. You see that this is indeed a tangent vector at the point Q to the manifold N, So let's maybe, draw a diagram to try to see it. Maybe this is the easiest way. So remember that the pullback goes from smooth functions on N, defined on N, into smooth functions defined on M. Oh, what happened here? On M, something like that. Well, P is up, just to keep the same notation, so something like this, right? So this is f star, the pullback, and now we take okay, an xp lies here, so I have an xp will be a smooth map here, right, into R. So when I'm taking the composite between xp and f star, what I get is something like this. So you see, this is xp composite f star. So this is the differential of f at p applied on xp. So this is indeed a map going from, you see, the set of all smooth functions defined from n to how we find the tangent vector. So as a first remark, this guy lies here. So the definition, at least from the point of view of the domain and codomain, is correct. We also need to check that this is indeed a tangent vector. So that this xp composed wave star, the differential, is indeed linear and satisfies the Leibniz rule. Now for linearity, that's pretty easy to check. For Leibniz rule, it's not complicated either. You just need to go and see what is differential of f at p applied on the product of two vectors, x times y, right? Well, this by definition is x, right? xy composite f star, right? Which is something like that. Is x, you see, x and p are tangent vectors, so they do verify Leibniz rule. So this will be eventually something of the form x. It will be the differential of f applied at xp times y plus x yp times the differential of f at p applies on yp, right? So both conditions hold, which means that this is indeed a tangent vector. So by this I mean that the definition is correct. Then let me go back to my. So here we were when, okay. So all right. Oops. Right. Okay, all these things that we were talking about. Okay, so here, right, I have the differential of a map. As I explained, you see, if the map goes between manifolds, then its differential will be defined between the tangent spaces, and it's correctly defined via the pullback. All right. Now, so here we already talked about this. Okay, we have properties for the differential, as I said, that the differential of the identity will be the identity of the tangent space at the point of a manifold. Chain rules apply, right? So you have the differential of composite is a composite of differentials, and also if f is a diffeomorphism, then the differential will be an isomorphism between vector spaces, with the inverse of the differential being the differential of the inverse. This property happens also if the map is not only a diffeomorphism, but also a local diffeomorphism. So it may be worth for me to write once what is this local diffeomorphism we keep talking about. So if from, let's say, the manifolds n into n will be and p, a point here, is a local diffeomorphism at the point P if there exists U open containing P such that the restriction of F to U, defined from U into the image to make it onto, is diffeomorphism. We are going to have some examples about diffeomorphism and local diffeomorphisms. So for now, you see, the interesting part is that we don't, for a map to be a diffeomorphism, right, that's a very heavy condition. Again, this means bijective, smooth, and the inverse smooth. Local diffeomorphism is a little bit easier to get to, and then it's enough for a map to be a local diffeomorphism in order for the differential of the function to be an isomorphism, a whole isomorphism. Okay, and now back to our tangent space at the point to a manifold, right? So we have the manifold, you have the point, the tangent the tangent space at P to the manifold, and we saw that this is a vector space. Vector space. So, because it's a vector space, we would like to see whether we can find a basis whether this vector space is finitely dimensional. So remember, we talk only about finite dimensional manifold. So the dimension is of dimension and finite dimensional. So we would like to check whether this vector space has a finite dimension, and if so, then we would like to find a basis for the tangent space. That's our next step. Now, what we are doing is the following. So I keep drawing this manifold. So you have a manifold because we see them better. So we take a point here. You see, every time you have a manifold and the point, you think local chart. So you take a local chart about the point. So this means, remember, please, this means that you have an open set about the point P together with a map F, which is a diffeomorphism between U and its image, phi of U. Right, we define local charts at the beginning, which is an open set of Rm. Okay, something like that. And then we just so we have a map going from, so you think of U as a manifold. Remember from the beginning of this course that every open set of a manifold is a manifold itself, and this is an open set of a Euclidean space, so a manifold also. So phi of U is a manifold also, with dimension m. So the dimension of the manifold is the dimension of the space it lives in. So m dimensional, and this is also m dimensional. It has the same dimension as the dimension of the manifold. So we look at this diffeomorphism. You see, at the restriction of the diffeomorphism, so you look at phi defined on U into phi of U. So this is a diffeomorphism. But if it's contained P belongs here, and of course its image belongs here, right? We have phi of P. But every time we have a diffeomorphism between manifolds, as we saw before, we can build up the tangent map, right? We can build the differential of this map, and for the case when this is a local diffeomorphism, then the differential, as we said, is an isomorphism of vector spaces. So this means what? This means basically that if I'm looking here and I'm taking the tangent space at the point P, so this is the tangent space. Let me see if I can get my colors, some color. So I'm taking the tangent space at P, right? Tangent space at P to U, which is, you see, is the same as the tangent space to P at P to the manifold M, right? The same thing, because U is just a subset of M, so the tangent comes there, and then we'll take the corresponding tangent space here, right? The tangent space at the point phi of P to this phi of U. Please remember that this is a subset of Rm, open subset. This is the same as the tangent f phi of P at Rm, is the same thing, and well, this is basically the same as Rm. This is the same thing as Rm, right? The tangent at Rm to a point is Rm. So we have something like this. So, and when we think about the map, taking this red vector space into the whatever purple vector space we have here, this is an isomorphism of vector spaces. But we know a basis here, right? We know the dimension here, and we can build up a basis for Rm. And so here, between these two vector spaces, you will have the differentiable of phi at the point P. So which is an isomorphism. So it has an inverse, it's a bijective, it has an inverse. You can go back, and we know that the inverse of this differentiable is simply the differentiable of the inverse, phi inverse at phi of P. So in fact, we know we take what we are doing practically in order to build up a basis for the tangent space at P to M for the red space there, is to look at the basis for this space, for the tangent space of Rm, basis for Rm, and to go back, you know, through the inverse of the differential to find the basis, to move this, to translate this basis, to push it back into the red space. So this is what we are doing here. So we are going to denote, right? So I'm going to write it properly here. So we have the differential of phi at the point P. This goes from TPM. This is what I draw on these things, right? On the diagram into T. We can take either this to be 0. It doesn't matter, because we can, you know, change the system of coordinates, make a translation there for Rm to take it into the origin. And now here we have a basis for this space, and we take this basis to be something like this, right? For I running from R to, so partial over, right? This is the basis for T0n, which is the same as Rm. Huh? So this is a basis. This is a basis for the space tangent at 0 to Rm, and then you see we go back to get a basis here. So we denote by something like this, simply the inverse, so the differentiable of P at phi inverse computed at this vector tangent at 0 to Rm, which is a vector of Rm, right? So we can do this for every I. So what we get is a basis for TPM, for the space tangent at the point P to the manifold M. So let me use these files. Okay, so here we are. Okay, this is very shortly what I explained you on that whiteboard, is that we take then a basis of Rm, and we go back to the inverse to find a basis on TPM. We call this also a mobile basis on TPM. It moves with the, we'll understand what this is about. So the basis, depending on the local chart, it depends on that diffeomorphism phi, right? So you cannot generalize for now that basis to the whole manifold M. It depends on the local chart, and then so that's a basis for TPM, right? So every vector, which is a tangent vector at the point P to the manifold M, can be expressed uniquely, right, for a basis of a vector space as a linear combination of this partial over partial xi, and with the property that you see when you apply the differential, right, on this f phi p, you will get ei. These are the standard vectors. This ei there. We'll have some examples there. So what conclusion can we pull out of this? How many vectors will we get on a basis of Rm? M vectors. So how many vectors will we get on a basis of the tangent space at a point to a manifold M? So this means that this is a vector space with dimension M. And in fact, we can prove, it can be proved, and we are going to explain a little bit how we do this. Okay. We're going to explain a little bit how we do this. The tangent space at the point M can be seen as we are going to put together all the tangent spaces, and we are going to build up a smooth structure there. So we are going to make something which is called the tangent bundle of a manifold, which will be a manifold itself. So for now, if M is an m-dimensional manifold, then at any point of the manifold, you can build up the tangent space at the point P of the manifold, and this is an m-dimensional vector space. And we can also find a basis for this. We know how to find a basis for this space using the it will depend on the local chart that we choose around the point P, and we can express every tangent vector as at P to the manifold M as a linear combination of those vectors. So again, it's important. The bases depend on the local chart that we chose. Now, another result here is that if you have two diffeomorphic manifolds, remember this means that there is a diffeomorphism between them, then they have the same dimension. This comes from the fact that if F is a diffeomorphism, then so I'm going to write this down because it's important. So if F defined from a manifold M to a manifold M is a diffeomorphism, then, or even a local diffeomorphism at some point P, then the two manifolds will have the same dimension. And then this comes from the fact, so, or a local diffeomorphism at some point P of M. This comes from the fact that when this happens, then the differential will be an isomorphism. So the differential of F at the point P is an isomorphism of vector spaces. But if M is of dimension M, that the dimension here will be M, and here with the same argument, the dimension is N, but an isomorphism will necessarily ask for the same dimension. All right, so you cannot have a sphere. You cannot have a sphere. All right, they do not have the same dimension. All right, so this is about the tangent space. Now we are going to build up, as I said, the tangent bundle of a manifold, and we are going to give it a smooth structure. So talking about the tangent bundle. The tangent bundle. So just for you to understand what I'm doing is the following. So again, I have a manifold M. I'm taking a point P, I can build a tangent space. I'm taking another point, I can build a tangent space, and so on. And then I'm going to put them all together. But I'm going to take the union of these spaces, but I'm going to take the disjoint union. So this means that, so this is something that we didn't know, so it's called by this disjoint union. So just to make sure that we know what we mean, an element here, you see, I'm attaching. You see, this is a union of tangent spaces to different points, or to all the points of the manifold, right? But so this is a union. A tangent space is a set of tangent vectors. So this is a set of all tangent vectors. So at every point, or at all points on the manifold, just to make sure that we understand that this disjoint one, I'm going to attach every. So every tangent vector to its origin. So I'm going to go with pairs like this PXP, where P runs over every point of M, and XP runs over all tangent vectors at every point of the manifold. All right, and now let me. Okay, so we can define a natural surjection, a projection map going from this T of M into M, in which every point here, so the tangent vector is taken into its, its origin, the point of M, right? At which it's tangent to the manifold M. Now, what will be the pi inverse, the pre-image of a point P? Well, this will give all tangent vectors at the point P, right? By the definition. So this is the same, if you want, is isomorphic with TPM. So right? So every point, if you want, every tangent vector is taken into the origin, right? So you take another tangent vector and so on, right? They all go to P. So the pre-image of that P will contain all tangent vectors at the point P to the manifold. So it's in fact the same thing as the tangent space at P to M. Now, again, our goal is to see that this T of M. So this is called the tangent bundle of a manifold. and this has a structure of a smooth manifold. We are going to see what an atlas on it is, on T of M is, and we are going to see what is the dimension of the. And now there are a lot of results here. I'm going to go to this thing to try to not get very heavy in computations. So sorry, we are here. No. Sorry. So tangent space, the tangent bundle, here we are. Okay. So, right. A lot of results here, but I'm explaining here how I'm taking how I'm building up the atlas on the tangent bundle, and I'm going to write it down on a white page just for you to see. So we have something like this. Okay. So we are going to take what is pi inverse. Okay, so we are going to take F, the following family of subsets of phi inverse of U alpha, where alpha runs over A. So by U alpha, I mean the domains. So M is a manifold. We talk about a manifold, and you have an atlas on manifold, which contains something like that, U alpha, phi alpha, where alpha runs over set of indices A, right? So this is what I mean here. So we take all these sets, right? Pi inverse of U alpha. Do you remember? I explained here what is the pre-image of a point there. So what will be in fact pi inverse of U alpha? What is pi inverse of an open set here? Well, using the definition of pi of this, so this is called a projection of the bundle, right? So this will contain all pairs like this of the form pxp, right? Such that pi of pxp is in U alpha. I think this is clear for everybody. It's set theory. So you will have tangent vectors together with their origin. When p runs over U alpha, it can be any point of this open, so remember U alpha, the point P, and such that xp is a tangent vector at the point P to the manifold M. But this is the same thing. It's like, you see, we can ignore that if you want that like P, and you can say that this is the set of all tangent vectors of M having the property that P belongs to the domain of the chart. So all the vectors, all tangent vectors here at any point of U alpha, right? So this will be pi inverse of U alpha. This will be they will give us the domains for the charts on the atlas that we are going to build on T of M, right? So let's define now. So remember, a chart is given by a set and some function, right? Some diffeomorphism. So we defined the domains. This will be our domains, and now let's define the maps, the homeomorphism, to be defined. So on the domain, right? Remember, a chart is something like this: phi, U and phi, where phi is defined on U with values in phi of U, which is some open subset of R M, whatever, when we talk about the manifold M. So I'm going to define it here with values in, well, I'm going to say something like this: is phi alpha of U alpha. Remember, phi alpha U alpha, it's a chart from the manifold M times Rm, something like this. And this will be a you see this one from the definition of a manifold for the manifold M. This is an open subset of Rm. So this total thing, this product, will be an open subset of R to 2M. And we define it like this, pretty intuitive. So it's pretty intuitive. So again, I'm applying tau alpha on an element of this set. What is an element of this set? Well, it will have vectors of this form, right? I'm taking the origin to make it clear. P xp by definition, if you want, definition. So this will be phi alpha of P. You see, so this first part belongs here. And on the second component, I'm taking the differential of phi alpha at P applied on the vector xp. So look here, okay? So this is phi alpha, u alpha, if you want. Now, so this is a map between manifolds, so it can talk about the differential. P belongs here, so we can talk about its differential, and it acts on T, P of u alpha, right? Tangent at P to alpha to the tangent of phi alpha of P to Rn, let's say, something like that, right? So this is the same as Rn. So when you take a vector here, xp, so xp belongs indeed, you see, in TPM. So here you apply TP u alpha, you apply the differential on this vector, and indeed, so this guy here belongs to phi alpha of u alpha, and the second part here belongs to indeed Rn, as we've seen here. So this is correctly defined, right, with the domain and the codomain. And now we are going to notice pretty easily that this is bijective. So 1 to 1 and on to, and its inverse, its inverse, which will go from phi alpha of u alpha times Rm into pi inverse of u alpha, will go like that, will be defined like this. This is pretty easy to check. You take some point here, q and y, right? And some element on that set, and this will be something like this, will be phi, so by the direct map goes into phi alpha of P. So now we go back, so it's phi alpha inverse of the point Q, and then so it's the inverse of the differential, which is the differential of the inverse applied on this vector, okay? And this is indeed something belonging to pi inverse of u alpha, right? Which, again, remember, we found it somewhere here, right? Pi, yes, it's here. Okay, so just to understand how this acts. All right, very well. And now it happens that we can build up an atlas on this tangent bundle. I didn't write it, I guess. Yes, this will be the tangent bundle. I did write it. And so we take the domains of the charts to be pi inverse of u alpha together with these maps, right? And for these so we define a chart for every chart, or chart on T of M for every chart u alpha phi alpha on M. Okay, so it's something like this. Now, I'm not going to prove this. That's a computation. If all the conditions to be checked is the fact that this is an atlas on T of M, which means that T of M, so Tm is the tangent bundle at the manifold M, is a smooth manifold. With dimension. So what is the dimension of a manifold? The dimension of a manifold is the dimension of the Euclidean space where you go, where the homeomorphism take the domain. So we look here, and this is 2M. So when M is a manifold, smooth manifold with dimension M, then the tangent bundle of the manifold is a smooth manifold as well, with dimension 2M. Okay, so twice the dimension of the manifold. Right, so let's see, let's go back to our file here. Okay, so this is what I'm explaining here. And you see, I did here the computations. I did prove indeed that this is smooth. I calculated that those transition maps for the tangent bundle, for the charts on the tangent bundle, and we use a proposition here, which allows us which allows us to use the fact that this tangent bundle is indeed, those initial conditions here for local Euclidean and everything. It's a Hausdorff space. It has a countable basis of open sets, second countable, we say it, and then you see this is the topology. The topology on T of M is the only topology. It's a topology for which the projection map. Remember that pi taking px p into the origin of the vectors of the tangent vector is continuous, right? So that's pretty important. So a lot of details here in computations, which are done. So again, you will have this file. I'm not going to insist because a lot of things to check, but we do have this unique topology for which this is a collection of charts. And then in what follows, you see, again, pi is continuous, as I said, right? And here you have I checked the fact that the space, the tangent bundle is a Hausdorff space. We need it, right, in the definition of a manifold, and so everything is checked here. Okay, so if M is an m-dimensional smooth manifold, then its tangent bundle is a two n-dimensional manifold, smooth manifold, and the projection is submersion. We'll see what submersion means. I'm going to talk about this in just a moment. Here we have the definitions of the charts. Now this triple here, as I said, is called the tangent bundle. We have the projection map, and this pi inverse of p, right? I'm going to show you that white page, that white board again, is isomorphic with the tangent space at p at the point at the point p to the manifold M is called the fiber over p. The fiber over p. Right. So. I'm going to go back to this one here, right? So let me just show you this. Okay, so here we did somewhere, yeah, so this part here, right? This part here, so this is what we call the fiber over P. The fiber over the point P of the manifold, right? This is isomorphic to the tangent space at the point P to the manifold. Very well. And now let's go and see. Let's go and see what is a submanifold. Any question here? Any question? Questions?
في أسئلة من المتدربين؟
Yes.
I ask them if there is any question.
Okay, sorry. Yes. So?
Because they can write, not use.
Yeah. So let me look at this chart. No, I think they say no. Okay.
Yes.
All right. Very well. Now we would like to see what is a submanifold. So let's go back here. No. Right. Very good. So in order to talk about submanifolds, we are going to talk about. Okay, so maybe I should do this before going to manifold. We have 20 minutes, right? 20 minutes more today. Okay, so maybe we do this. I think it's better, okay? Because I keep talking about manifolds, but I never compute manifold about the differential of a function, but I never compute the differential of a function. Let's take some examples maybe, right? Today, and then we'll go to submanifolds tomorrow. Okay, let me come here. All right, so, right, you have some examples on that file. So let's see. Okay, so for instance, let's take F. defined on R cube into R. I'm starting with a simple example, defined by f of xyz equals, then I'm taking x squared y plus 2xy cube plus z squared. Okay, so you see, in order to write down the differential, write down the differential of a function, I need to write it in the local chart. So what is the differential of f at the point P? Is the differential of the local representation of f in the chart f psi. Remember, this is psi composed to f composed to phi inverse, computed as phi of p. So this is what we are using, right? Okay, so we need to, so this for the general case, when you have a manifold and another manifold, this is the point P, this is f of p. Here you take a chart u phi, and here you take a chart v psi. Okay, it's something like this. Okay, now, so for this particular example, the manifolds are Euclidean spaces, R cube and R. So the charts, when you look at this, at your function, the charts are the identity. Here you take the whole R3 with the identity, and here you take the whole R with the identity. So when you get and write down this local representation, you will get the F, right? So in fact, in order to write right, I'm going to say the matrix, for instance, right, of the different, this is a linear map, the differential, right? So it can be represented by its matrix. So what is the matrix of the differential of f at p? Well, it's simply the matrix of the partial derivatives. So there's the derivative of f, so partial derivative of f with respect to x, partial derivative of f with respect to y, partial derivative of f with respect to z, right? So that's 2xy plus 2y cubed, right? Then with respect to y, x squared plus 6xy squared, and with respect to z, that's 2z, right? I think that's pretty clear. Okay, now if the function, so that's one example of how we write the differential. Now, if the function would be defined like that, right? So again, these are Euclidean spaces. The homeomorphism of the maps are the identity. So the matrix of the differential of f at p, that's simply the Jacobi matrix. So f phi psi is f identity, right? So it's f. So this is the Jacobi matrix of f, right? So this will be, so compute the partial derivative. So that's 2 with respect to 2xy plus 2. So 2xy. I didn't take a function, right? So the function would be f of x, y, z. I'm just taking a random function. I didn't write it, x, y, z squared, right? We define it like this. So differential with respect to x, 2xy plus 2. Then with respect to y, that's x squared. With respect to z, that's a 0. Then with respect to x, that's y, z squared, right? With y, x, z squared. Z 2x, y, z, right? So we have something like this, the matrix of the differential. Now, the interesting, maybe less known case would be if we have a function. Let me see if I can find a function defined on, yes, so let's take a function defined on manifolds which are not Euclidean spaces. So I'm going to take f defined from Sn into Sm, so n-dimensional sphere onto n-dimensional sphere defined like that, f of, so a point here will be of the form u1, u2, un plus 1, and we take, I'm assuming that n is less than or equal to m, so I have some extra coordinates there in m, which I'm going to take to be 0, all of them, something like that. Okay, so I'm taking minus here, minus. Okay, so here we have how many zeros? M minus n, right? M minus n zeros. Right? So we would like to find the differential, the matrix of the differential of f at some point q. So what is this? I need to write down the map f in local charts. So this is the differential of, I'm going to work with those stereographic projections, right? So I'm going to take phi s, phi n, okay, something like this, at the point phi n here of u, right? So I'm taking a point u on Sn, and I'm going to, so remember we have to chart here the Sn minus North Pole, Sn minus South Pole. Let's say that u belongs to un, right? So this means that u is not the North Pole, right? So the last component of u is not -1, right? So f of u will be in US, you see? No, this is plus, the North Pole. So if un plus 1 is not 1, this means that negative un plus 1 minus un plus 1 will not be -1. So this point here cannot be the South Pole. So I can see f of u in the south in the other chart, right? So I'm going to take, so I'm going Sn into Sm. Here I'm taking the chart un together with that phi n, right? And this is US, so the sphere without the South Pole together with this one. And then I need to write the local representation of f in this chart. So this is phi s composite f composite phi n. Okay, and when you go and calculate this, so this will be defined like this. All right, this is the subset of Rn, and this is the subset of Rm, right? As the function is defined like that. And then I'm going to call it G to, spare some time. So G applies on a point here, so on a point of the form y1, ym. And then this will be, I forgot the -1 here. So this is what? This is phi s times f of, and phi n inverse will be, if you remember, 2i1 by 1 over 1 plus, I'm going to denote it by something like this, it goes faster, and then 2yn, and the last one is the norm of y squared minus 1 over 1 plus the norm of y squared, something like that. And then now this is phi s, so I'm applying f here, so f, you see, take some zeros here, n minus n zeros, and then put a minus in front of everything else. So this is 0, 0, then you have minus 2i1 over 1 plus length norm of y squared, negative 2in over 1 plus norm of y squared, and 1 minus norm of y squared over 1 plus norm of y squared, something like this. And now here I'm applying phi s, right? If you remember, it's something like this. So the first will be 0 because it's 0 over something, so 0, 0, 0. And then you divide every component by the last one, by 1 plus the last one. This is why it's every component over 1 plus the last component, y, whatever, z n plus 1, z n, so over this one. So this is negative 2y1 over 1 plus norm of y squared over 1 plus 1 minus the norm of 1 y squared over 1 plus the norm of y squared, and up to minus 2yn over 1 plus the norm of y squared over 1 plus, again, 1 minus the norm of y squared over 1 plus the norm of y squared. Okay, and when you do some algebra here, you have 0, 0, and then you get minus y1, simplifies very nicely, up to minus yn. Okay, so in fact, the matrix of the differential of f at some point q is the matrix of the differential of this g, right, and the local representation of f in the local charts at y. So what is this? So first you will get only zeros here, right? 0, 0, 0, 0 for the first component, and then you'll get a -1 and everything else is 0, then you have 0, -1, everything else 0, 0, 0, -1, right? Something like this. So if you want to have a 0 matrix here, it has m minus n rows and n columns, right? And then here is minus the identity matrix of over n, right? So in order to write down differentials, you will need to if the map is defined between manifolds, you will need to go and write local representations of the function in local charts. And let me show you another example. Do I have time? Okay, let me try to show you. Yeah, maybe 5 minutes, 7 minutes, 6 minutes. So let's take the following function, f from r squared into r squared, talking about a little bit about tangent vectors here. So I'm going to define the function I did, f of xy. That's a nice example, and we are going to see a little bit later again. So that's cosine of alpha, negative sine of alpha, sine of alpha, and cosine of alpha times xy, right? So I'm writing it as a matrix, in the matrix form, these functions. Now we would like to find, so let's see what is the differential of f at the point P computed at some vector xp. Remember, if f runs from m to n, then the differential of f at the point P runs from the tangent space at P at M into the tangent space at f of P at the manifold. So it applies here on a tangent vector. So we would like to see what is this, where P is a point of r squared, we are in r squared here, and then xp is the following tangent vector, minus y partial x at P. Remember, that's the basis for the tangent space, partial over partial y. So I want to compute the differential of f at P at this particular tangent vector. Okay, so let me remind you very, very quickly. So again, if you have I'm writing the general notions here for this particular case, so that the differential of f at P runs from what? From the tangent space at P to r squared into the tangent space at f of P to r squared. Okay, so what is the basis here? The basis will be given by partial over partial x at P, partial over partial y at P. And remember, this is, we talked about the basis for the tangent space. They are the inverses of the they are the images through the inverse of the differential of the local, of those homeomorphisms of the local chart of the basis of r squared. And here we have a basis also. I'm going to call it d partial over partial u at the point f of P. They depend on the chart, but here we have r squared, so the chart is the identity at f of P, right? It's the same chart everywhere. Okay, now what will be, so if you calculate f of x and y, if you go and multiply those two matrices, right, what you get is cosine of alpha times x minus sine of alpha times y, and plus sine of alpha times x plus cosine of alpha times y, right? Something like that. So what is the matrix of the differential of f at P? Well, do you remember that this is the matrix of the partial derivatives? So this will be, so when you compute the derivative, you will have cosine of alpha with respect to x, cosine of alpha, and then with respect to y, minus sine of alpha, with respect to x, sine of alpha, with respect to y, cosine of alpha. I think that's clear for everybody, right? And then what will be the difference? So I want to see, so remember, we'd like to calculate, to compute an expression, where is it, for the differential of f at P at a given vector, right? So let's see, what is the differential of f at P at a given vector? So this is at xp, this is the differential of f at P. I'm going to write this vector here because I don't see it. So it's minus y partial over partial x at P plus x partial over partial y at P. Okay. Let me see, yeah, I'm finishing in 2 minutes. So now, do remember please that the differential of f at P is linear. Differential is a linear map. So this will be minus y differential of f at P calculated at partial over partial x at P plus x differential of f at P calculated at partial over partial y at p. All right, so that's because of the linearity of f. Now this will be minus y times, now what is this? This guy will be partial. I'm going to, okay, denote this. I'm going to call this f1, and this f2, okay? So I'm making something easier. So this will be what? This will be partial f1, the partial derivative of f1 with respect to x, b partial over partial u at f of p. I'm writing it as a linear combination of the vectors from the basis of the codomain plus this times partial over partial v at f of p. Right? Something like this. And then plus, I'm looking at the second part. Now I'm here. This will be x, then partial f1 over partial y, partial over partial u at f of p, plus partial f2 over partial, this is x, sorry, this is x, partial y times partial over partial v at f of p. Okay, and now let's go and see what is this equal with. Equals, so it's minus y. When you go and compute, you'll have partial f1 with respect to x. So this one with respect to x is cosine of alpha. Okay, partial over partial u at f of p. f2 with respect to x. f2 with respect to x, we are here, right? Sine of alpha. I have a minus y sine of alpha minus yes, x sine of alpha, y sine of alpha, partial over partial v at f of p. Then I'm coming here, right? With f1 with respect to y is minus sine of alpha. So this will be minus with an x in front, minus x sine of alpha partial over partial u at f of p. And I'm here plus, I have an x, I'm here, f2 with respect to y is here, that's cosine of alpha partial over partial v at f of p. And I'm arranging it, right? The basis is given by partial over partial u, partial over partial v. So I'm just arranging it, and I get minus y cosine of alpha from this one, and minus x sine of alpha, the coefficient of partial over partial u f of p. I'm writing this vector as a linear combination of the vectors from the basis. That's why I'm doing from the basis of the codomain. So here, okay, of these ones. And then this is minus y sine of alpha, and plus this plus x cosine of alpha partial over partial v f at f of p. And that's how we compute differential of a function at a point computed at some tangent vector. And it's 8 o'clock. Any questions?
في أسئلة متدربين؟
Questions?
Maybe there is no question.
Okay. I have a chart here. No, thank you. We are welcome.
Thank you, Doctor, for the wonderful presentation of the Riemannian geometry today. Inshallah, we will complete tomorrow, بإذن الله.
Sorry?
Inshallah, we complete. Thank you, Doctor. Inshallah.
Yeah, we'll continue tomorrow. Yes, of course. Thank you.
Thank you for you, Doctor.
All right. Bye.
باي دكتور. إن شاء الله نكمل غدا. رابط الحضور أرسلته سابقا. سبحانك اللهم بحمدك أشهد أن لا إله إلا أنت أستغفرك وأتوب إليك.